Okay, this is a potential energy diagram. It shows you over time during the reaction. So the start of the reaction is always over on the left, on where the X and Y axis meet, and the end of the reaction is where the line stops. Over time, how much energy is involved? Don't get hung up on the word potential. It applies to everything. So just how much energy is fine. So let's just work through these and see if we can figure out a way to make sense of this graph here. First of all, reactants. Reactants are at what part of the reaction? Reactants go to products. So reactants are what you have to begin with. That's what you start with. So those would be at the start of the reaction. I'm going to use a capital R to represent that just because this is a pretty small graph for me to try and write on. So that would be the flat part at the beginning there. So in this case, 80. And it's usually kilojoules. I didn't label mine, so I wouldn't count it wrong if you didn't either. But usually it's measured in kilojoules. So if you want to label, put a KJ. Okay, and the products, as we can see over here, are at the end. So, and we'll just label those P. So those would be down here at this flat part. So for the number for this one, it would be 120. So, just go over from here. 120 kilojoules. So those are pretty straightforward. The activated complex, let me explain kind of what that is. That is when two atoms or molecules run into each other. For a split second, they're all there together. It's very, very high energy, and it will not last. They will either bounce off of each other and go in opposite directions, or they will react and the new things will go in opposite directions. But for that split second, you have this great big molecule. It's just a big blob of atoms with really super high energy. So for activated complex, the key word or key phrase here is high energy. So it's going to be the top of the hill, and I'm just going to use AC for that activated complex. So the AC for this reaction would be just slightly above 260, so it's probably 265 kilojoules. Now the activation energy is how much energy it takes to make that reaction happen. How much energy does it take to activate the reaction? But remember, you're not starting at 0. You're starting at however many your reactants have. So for that reaction to happen, you need to go from the 80 that we currently have up to the 265, which is the max we're going to need. So your activation energy is going to be the uphill version of our graph. So our activation energy, the way that we find it, if you want an equation, is you take the activated complex minus the reactants. So we would take 265, I'm out of space, I'll put it over here. This is for activated complex, 265 minus 80. So that would be 185, so 185 kilojoules. So that's how you find the activation energy. The heat of the reaction is the difference between how much energy it has at the very beginning and how much energy it has at the very end. So there isn't really a line on here, but we can draw a line on here showing that part. It would be this part here. I made it in fluorescent pink so you could see it. That is your heat of reaction, delta H. Change in heat. And you get that by taking your products minus your reactants. So our products were 120 minus our reactants of 80 gives us 40 kilojoules for our heat of reaction. So it's basically the change in energy from beginning to end. Now, if that same hill is going uphill, like, all right, so right here, if this is going uphill, then that is an endothermic reaction. If it goes downhill, so this is endo, if that were to come downhill, that would be exo. So it's the delta H's line, and that determines it. So this one is endo. Now, if we had a catalyst, that would basically start at the same place. A catalyst, by definition, cannot actually be a reactant or a product. So those two things have to stay the same. So what a catalyst does is it finds a shortcut to get to the same place. So you start at the same place, you end at the same place, but basically, ultimately, it lowers the hill down. So your activated complex is way down here now instead of way up here. So it lowered the activated complex. It also then lowered the activation energy because that's over here. It lowered one more thing, but to do that we have to look at the reverse reaction. So for right now, we'll just go with that. Okay, this is literally looking at the back of my paper. If you pick your paper up and hold it up so that there's a light behind it, you can see the graph from the reverse angle. So what this is talking about is if we made our products reactants and our reactants products and we went backwards, we tried to undo the previous reaction. And so looking at it from the back, if you put reactants here and products here, put your finger on one of those, flip around to the other side, what's it equal? So if you put your finger on the R and you flip it over, what is it on now? It should be on the products of the forward. So your activated complex does not change. It's still the top of the hill. Remember, this was the activation energy of the forward. So looking at it from the backward angle then, this becomes your activation energy. I don't know why I didn't just put AE of the reverse. So if you put your finger on that and flip it over to the other side, I better let you write it first. Put your finger right on that, flip it over to the other side. That ends up being right here. So the downhill part of the front is the activation energy of the reverse. Now the reason I point that out is because that is also changed by the catalyst. So the catalyst changes the activation energy of the forward, the reverse, and the activated complex. So that kind of gives you an insight into that. Now, I'm going to give you some homework that you can try with questions about each of these. So I gave you some notes on how to figure it out. Let's see what you can do.